Hello everybody, this is Dr. Christopher White here, and today we are moving on to lecture number 4, which will be dealing with rocks. As you can see, this lecture will be coming to you in 2 parts. So today we're going to do part 1, which will focus on igneous and metamorphic rocks. Okay, so before we begin, a key point to remember, of course, and this is something that constantly gets forgotten, rocks consist of one or more minerals. Okay, minerals are not rocks, minerals are what make up rocks. It's a common mistake that keeps getting repeated again and again and again. So, as I'm sure you remember, rocks are split into, well, it's debatable actually. Rocks can be split into 3 or 4 groups. So there's obviously the groups you are familiar with, igneous, metamorphic and sedimentary rocks. And then you can see at the bottom there's the 4th group, hydrothermal. So igneous rocks are, of course, any rock that forms from a magma or lava. Essentially the cooling and solidification of that magma or lava to form a solid rock. Metamorphic rocks are the result of changes in pressure and temperature. So as the pressure and temperature goes up or down, certain minerals become stable or unstable, and as they become as minerals become unstable, they can do one of 2 things. They can melt, or they can change into a completely new mineral that is stable at the new pressure and temperature. Now, in the case of metamorphic rocks, I'm sure you remember, a metamorphic rock can only form if the rock that's changing does not melt. As soon as the rock that's changing starts to melt, we go into the igneous regime. And then we have sedimentary rocks. Those are rocks that are formed from either particles of eroded rock through the direct precipitation of minerals like carbonate from seawater, or through the evaporation of large bodies of water producing evaporites. Now, the question is why is hydrothermal at the bottom, and why do I feel a little bit uncomfortable calling it one of the groups of rocks? Well, the problem is hydrothermal processes are intimately related to igneous, metamorphic and sedimentary rocks. So in the case of metamorphism, it's not uncommon for hydrothermal fluids to be circulating around as part of the metamorphic process, and those hydrothermal fluids will alter the rock and metamorphose it. So metamorphic hydrothermal rocks are not at all uncommon. Same with igneous systems. So in igneous systems, it's not uncommon for magma, as it cools underground, to release water into the surrounding rock. So in that situation, you have a hydrothermal fluid that's essentially circulating around and is being put into the surrounding rock from the igneous body. So it's not uncommon to have igneous hydrothermal rocks. And then you have sedimentary hydrothermal rocks. That's when you have trapped water within sediments that are being buried and compressed and liquefied. Well, obviously, as that sediment gets buried deeper and deeper, the water that's trapped in that sediment is exposed to higher and higher temperatures. And eventually it becomes a hydrothermal fluid. And so you have hydrothermal fluids that circulate around in response to sedimentary processes, and they will deposit minerals, typically due to some kind of temperature change or fluid mixing. So hydrothermal rocks are intimately related to igneous, metamorphic and sedimentary processes. So I always find it a little bit dodgy to say that there is a 4th class of rock, but some people believe that hydrothermal rocks should have their own separate group. So just be aware of that. So I'm sure you remember rocks are part of the rock cycle. So the rock cycle essentially covers the destruction of old rock to make new rock. Now, of course, obviously, when you make new rock, you obviously must destroy old rock. If you didn't, the Earth's crust would effectively keep getting larger and larger and larger. And that just doesn't work. So when we make new rock, we have to destroy old rock. So how does the process work? Well, the process begins with magma being erupted onto the surface, where it cools, and it forms topographic heights, essentially volcanoes. Those volcanoes will be weathered. And so that's the process of weathering, is the process of breaking up the rock into chunks. Those chunks that are produced will then be eroded. That's the process of taking those chunks of rock and turning them into smaller particles that can be transported by water, ice, wind, or gravity. So the sediment, essentially all these loose particles of rock, will be transported until whatever is transporting them loses the energy to move them. And so once the transporting medium no longer has the energy to move the particles, it will deposit them. And over time, layers and layers of sediment will be deposited one after another, after another, after another, after another. And so this means that the layers of sediment at the bottom of that pile of layers of sediment start getting buried deeper and deeper and deeper as new layers of sediment are deposited on the top. So this means that the layers of sediment at the bottom of the pile start being exposed to higher temperatures and higher pressures. So what this means is the sediments will initially undergo the process of compaction. That's when the layer of sediment gets compacted, squished. And eventually it will undergo the process of cementation or cementation. And that's when the particles in the sedimentary rock get stuck together by minerals which precipitate in the pore spaces. And once your rock is cemented, essentially it's been lithified and it is now a sedimentary rock. Now, one of a couple of things can happen to that sedimentary rock. It can be uplifted above sea level, it can be eroded to produce more sediment that gets transported, deposited to produce a new sedimentary rock. If, however, that sedimentary rock keeps getting buried, so it keeps carrying on down here, obviously, as it gets buried deeper and deeper in the earth, it will be exposed to higher pressures and higher temperatures. That will cause the minerals in the sedimentary rock to become unstable, and they will begin to change into new minerals that are stable at the higher pressures and temperatures. Metamorphism. So your sedimentary rock will eventually follow this path here, if it's not uplifted, and it will turn into a metamorphic rock. So what can happen then? Well, obviously the metamorphic rock could be uplifted, exposed, weathered, eroded, transported to sediment produced, transported, and deposited to produce a new sedimentary rock. Or the metamorphic rock could have one of a couple of things happen to it. It could keep being buried until the temperature reaches a point where the metamorphic rock melts. Or it could be exposed to a igneous intrusion in the crust, which heats up the metamorphic rock sufficiently to the point where, once again, it starts to melt. So anyway, the metamorphic rock can, if it's not uplifted, will eventually be exposed to higher temperatures and or higher pressures, and it will eventually reach the point where it will begin to melt, at which point the minerals in the rock will go from being solid and they'll turn into a liquid. Of course, once they start melting to form a liquid, you have a magma. Now, of course, magma is naturally buoyant compared to the surrounding rock, so like a helium balloon, it will want to rise. So any magma produced will naturally start rising through the crust. Now, about 90% of all magma will never make it to the surface. It gets stuck in the crust, where it crystallizes as very, very coarse igneous rocks we refer to as plutonic igneous rocks. Or the remaining approximately 10% will make its way to the surface, where it will be erupted out onto the surface of the Earth through volcanoes. Obviously, once again, these igneous rocks can then be uplifted, exposed to the atmosphere, weathered, eroded to produce a sediment. That sediment can be transported, deposited, where it will produce a new sedimentary rock. So essentially that's the rock cycle. I'm sure you guys are pretty familiar with it from physical geology, but I figured it was worth just going over it again just to cover those basic points. Alright, so to start with, let's think about igneous rocks. So igneous rocks are split into two broad groups. There are the intrusive or plutonic igneous rocks. These igneous rocks are coarse to medium grained, and they are formed by slow crystallization underground. Then we have extrusive or volcanic igneous rocks. They are essentially they have very, very fine crystals all the way to glass. That's when there are no crystals at all. They're formed by rapid crystallization, very rapid cooling, at the Earth's surface, and they occur both on the continents and on the sea floor. So typically when we think of volcanic rocks, our mind instantly goes to volcanoes on land. We think of volcanoes like, Mount St. Helens or Vesuvius. However, we have to always remember that a lot of volcanic rocks, a lot of magma, a lot of lava is actually erupted onto the sea floor, and we never see it taking place, but nevertheless it is happening. Okay, so molten rock is often referred to as magma, but it's also referred to as melt. And now this is one of the things that might happen Typically, when you do grad schooling in geology, you'll often stop referring to something as a magma and you'll start referring to it as a melt. I will do my best to refer to a liquid rock as a magma. However, every once in a while I might refer to it as a melt. That one's on me, I do apologise. So magma is typically dominated by silica, silicon, SiO2. So most magmas are what we refer to as a silicate magma. And silicate magmas will crystallize out silicate minerals like olivine, pyroxene, feldspars, amphibole, biotite, etc. So most magma is generated at depth due to deep burial, subduction, or mantle melting. The generation of magma at very, very shallow depths in the crust is, relatively rare. So if a magma erupts onto the surface of the Earth, it's referred to as lava, a term which I'm sure you're familiar with. And as I'm also sure you're familiar with from physical geology, the melt composition, the chemistry of the melt, and the temperature of the melt controls the types and composition of the minerals that will form. Okay, so let's start off by looking at this diagram. We're going to focus up here to begin with. I'm sure you remember from physical geology, but there are 4 classes of magma, essentially, and they're based on the chemistry of the magma. There's felsic magmas, intermediate magmas, mafic magmas, and ultramafic magmas. So what we're going to do is we're going to ignore all of this bit here to start with. I'm going to go down to these arrows down here. So you can see as you go from felsic to ultramafic magmas, the first thing you'll notice is the temperature of that magma goes from about 700 to 750 Celsius for a felsic magma, all the way up to around 1400 for an ultramafic magma. Maximum temperature from an ultramafic magma is actually somewhere in the region of 1600 Celsius. So as we go from felsic over to ultramafic, the temperature of the magma is increasing. Now obviously the fact that the temperature gets higher will affect the types of minerals you get. Obviously ultramafic rocks will be made up of very high temperature igneous minerals. In contrast, those high temperature igneous minerals will not occur in felsic rocks because the temperature is too low. So in the case of felsic rocks, you're going to end up with minerals that are stable at lower temperatures. So what else changes? Well, depending on what's actually melting to form the magma, the composition of the magma will change. So in the case of mafic and ultramafic magmas, what is melting to make that magma are mantle rocks. Mantle rocks are dominated by olivine, which is an iron magnesium silicate, pyroxene, which is an iron magnesium calcium silicate, and calcium plagioclase feldspar, which is a calcium silicate. So this means that when you melt mantle rocks to make an ultramafic or mafic magma, the magma you produce is going to be rich in iron, magnesium, and calcium. So mafic and ultramafic magmas are rich in these 3 elements compared to felsic and intermediate magmas, which form from different material, and therefore they have far less iron, magnesium, and calcium in them. In the case of felsic and intermediate magmas, what's melting tends to be the crust, most commonly the continental crust, but occasionally sometimes the oceanic crust. And so because the continental crust and oceanic crust has a completely different composition compared to the mantle, it's going to give a magma with a different composition. So when you start melting continental crust especially, you end up with a magma that's very, very rich in sodium, potassium, and also silicon and aluminum. But for the time being, we're just really worried about sodium and potassium down here. So the compositions of these magmas will also change. As we go from left to right, the amount of iron, magnesium, and calcium is increasing. As we go from right over here to left, ultramafic to felsic, the amount of sodium and potassium is increasing. Once again, that's going to affect the types of minerals we get. So ultramafic and mafic igneous rocks are going to be rich in iron, magnesium, and calcium minerals because that's what's there to actually make the minerals in the first place. In contrast, felsic and intermediate rocks are going to be rich in sodium and potassium minerals because, once again, that's what's actually there to make minerals from the magma. So you might remember when we discussed these 4 types of magma, we also discussed the classic volcanic and plutonic rocks that form from them. So along the top here we have the classic volcanic rocks that form from these four types of magma, and along the bottom here we have the classic types of plutonic igneous rocks that form from these four types of magma. So for volcanic rocks, felsic gives you rhyolite, intermediate gives you andesite, mafic gives you basalt, and ultramafic gives you a type of rock called a komatiite. In terms of plutonic igneous rocks, felsic magmas give you a granite, intermediate give you a diorite, mafic give you a gabbro, and ultramafic give you a peridotite. Now, to be clear, rocks like rhyolite and granite have exactly the same composition. So if you took a lump of rhyolite and a lump of granite and you melted it down so you just had a liquid, a magma, the composition of that magma would be exactly the same. The only difference is that these rocks up here have cooled very, very quickly, so they end up with very, very fine crystals, hence the fact they're called volcanic. In contrast, these four rock types here are formed from a magma that's cooled very, very slowly, hence the fact you end up with coarse crystals, so they're classified as plutonic. That's the only difference. Now, underneath all of this, what we see is a diagram here, and this diagram allows you to predict the types of minerals you would expect to get from each type of magma. So over here in the ultramafic field, so we're going to come down, we're going to look at this rectangle here. Ultramafic rocks are mostly dominated by olivine, with a little bit of pyroxene. In contrast, mafic igneous rocks are going to fall somewhere in this region about here. They're going to have a significant portion of calcium plagioclase feldspar, a lot of pyroxene, a little bit of olivine, and maybe even a smidgen of amphibole, possibly even some biotite mixed in there. Andesites and diorite are going to fall mostly in this field here. So you're going to get lots of both sodium and calcium-rich plagioclase feldspar, a little bit of quartz maybe, muscovite, biotite, and amphibole, maybe a little bit of pyroxene. And then finally we have the felsic igneous rocks over here. They're going to be dominated by orthoclase, that's potassium feldspar to you and me, quartz, a little bit of sodium plagioclase feldspar, muscovite, biotite, and possibly some amphibole. So essentially the composition of the magma and the temperature of the magma affects the minerals that we get. Over here we have the high temperature minerals, over here we have the low temperature minerals. So this is summed up by the Bowen's reaction series. So these are high temperatures up here and low temperatures down here. So as we go down the diagram here, the temperature is decreasing. And here we have the four types of magma: ultramafic, mafic, intermediate, and felsic. And we can see that as we go down through these four fields, the types of minerals change. That's a result of the changes in temperature and the changes in the magma composition. So once again, up here for ultramafic magmas, we have lots of olivine, a little bit of pyroxene, and a little bit of calcium plagioclase feldspar. I should say the amount of the arrow that's in each of these fields corresponds to the amount of the mineral you would expect in the rock. So in the case of an ultramafic rock, as you can see, most of the olivine arrow is in the ultramafic field, and so you'd expect the rock to be very, very rich in olivine. So then we have mafic igneous rocks. They will give you a rock that's dominated by a lot of plagioclase feldspar and a lot of pyroxene, with maybe a little amphibole and possibly a little bit of biotite. Intermediate magmas will give you a rock that's dominated by more sodium-rich plagioclase feldspar, a lot of biotite, a lot of amphibole, and maybe a little bit of pyroxene, whilst felsic igneous rocks will give you rocks that are mostly dominated by potassium feldspar, muscovite, quartz, and maybe a little sodium plagioclase feldspar, a little bit of biotite, and a little bit of amphibole. So the Bowen's reaction series just kind of sums up what you would expect from each of these four different types of magma in terms of what minerals you should see. So igneous rocks can be separated based on their crystal size. So very, very coarse igneous rocks, so that's rocks that have a crystal size in excess of 20 millimeters, that's 2 centimeters, are classified as pegmatitic. Coarse-grained igneous rocks with crystals in excess of 1 millimeter in size, up to 20 millimeters in size, are referred to as phaneritic. And fine-grained igneous rocks with crystals smaller than 1 millimeter in size are classified as aphanitic. So plutonic rocks are typically either phaneritic or pegmatitic because the magma cools slowly underground, producing coarse crystals. In the case of extrusive igneous rocks, the magma is erupted onto the Earth's surface in the form of lava, which cools quickly because the air is comparatively cool. And so because the magma cools quickly, it means the crystals are very, very fine. And so the vast majority of extrusive igneous rocks are aphanitic in their makeup. So to show you, so here is a pegmatite. So you can quite clearly see, look at the size of these crystals. You can see you've got these really big potassium feldspar crystals here, some very, very large quartz crystals here. The largest crystal I ever saw in a pegmatite was somewhere in the region of about 10 to 15 feet in size. So they can get extremely large. Now compare the pegmatite over here to a granite. You can see that in the case of the granite, the crystals are easily visible. You can see them with the naked eye. However, they are less than 2 centimeters in size. And now compare that to this aphanitic rock up here, this lump of basalt in this picture. You can see that there are no visible crystals in this sample whatsoever. The only way you can see the crystals is if you look down a microscope. When we look down a microscope, what do we see? Well, we see that basalts are mostly made up of these thin, slender grey minerals here. That's plagioclase feldspar. And these kind of neon-coloured minerals here. That's pyroxene. So if an igneous rock has a consistent grain size, it's termed equigranular. So in the case of this granite here, we can see that all the crystals are approximately the same size, so we would describe that as an equigranular granite. Now, if an igneous rock has two different crystal sizes, it's termed porphyritic. And that's the result of two-stage cooling, and we're going to discuss what that actually means in a second. So when you look at a porphyritic rock, what you'll notice is some of the crystals are rather large compared to the vast majority of the crystals in the rock. So here we have a plutonic porphyritic rock. Here we have an extrusive porphyritic rock, a volcanic porphyritic rock. So in the case of this granite here, we can see we have these rather large pinky red-coloured, salmon-coloured potassium feldspar crystals. And they are considerably larger than the quartz crystals and plagioclase crystals and the biotite crystals that make up the vast majority of the rock. So these coarse crystals are referred to as the phenocrysts, and the smaller crystals that surround the phenocryst is referred to as the ground mass. So if we look over here at this andesite, we can see we actually have two different types of phenocryst. We have these lighter coloured feldspar phenocrysts here, and these slightly darker coloured phenocrysts here. It's a little bit difficult to tell what they are. They could be anything from quartz to amphibole maybe. Okay, but you can see you have two different phenocrysts, and both of those phenocrysts are sitting in this very fine-grained ground mass. So yeah, so just be aware that you can have more than one mineral forming phenocryst in a sample. And in the vast majority of cases, porphyritic rocks do tend to be volcanic. Most plutonic igneous rocks will tend towards equigranular. So we'll just quickly discuss two-stage cooling, then we'll have a break. So two-stage cooling is caused by some of the crystals, the coarse crystals, the phenocrysts, forming by slow cooling underground, whereas the ground mass forming by more rapid cooling slightly closer to the surface. So here's our model. So in the crust we have a big ball of magma stuck in the crust. That's our intrusion. Now this intrusion is cooling down, and eventually it starts to crystallize out a mineral. So in this case the mineral is these grey squares. So that's the mineral that starts crystallizing out down here in the intrusion. Now, it just so happens that the intrusion is nice and warm, it's cooling slowly, so these crystals of the grey mineral grow nice and big. Now, when the magma from this magma chamber up here moves up into this smaller staging chamber up here that feeds a volcano, some of the grey crystals get swept along with the magma as it moves from this big magma chamber here into this staging chamber here. Now in the staging chamber, the temperature of the magma continues to drop, and eventually it starts to crystallize out these green minerals as well. Now those green minerals are also forming underground. The magma is cooling slowly, so they also get quite large. So then what happens is when some of the magma from the staging chamber gets swept up towards the surface to be erupted out of a volcano, well, understandably, some of these grey minerals and some of these green minerals also get swept up along with that flow of magma, which then gets erupted onto the surface as lava, and obviously the liquid portion of the magma cools very, very quickly, forming a fine-grained rock which contains these much larger crystals of the grey and the green mineral, and you end up with something that looks like this. And so that's two-stage cooling. Essentially, it says one part of the cooling occurs underground slowly, and one part of the cooling typically occurs on the Earth's surface or very near the Earth's surface, and that portion of cooling occurs rapidly. Okay, so we've been going for 25 minutes. Time for a quick break. Pause the video, get up, have a walk around, go and get yourself a glass of water, and come back to me in a few minutes. Okay, everybody. So this table here just very quickly summarizes some of the key features about the 4 different types of magma. So obviously here we have felsic, intermediate, mafic, and ultramafic. Just a quick side note, if you happen to look at old textbooks, so if you do happen to study geology at university, typically you'll have to use old textbooks at some point, and you might notice that felsic igneous rocks are referred to as acid, mafic igneous rocks are referred to as basic, and ultramafic igneous rocks are referred to as ultrabasic. Now, these 3 terms are the old terms. They're not really used anymore, but just be aware they are out there in the literature. Okay, so as we can see, as we move from felsic to ultramafic, we can see quite clearly the temperature goes up, the amount of silica goes down. So that means the minerals we form are very silica-rich in the case of felsic igneous rocks, there's so much of it, and very silica-poor in the case of ultramafic rocks because there's so little of it. In the case of felsic igneous rocks, they can form the ultimate silica mineral, which is, of course, quartz, which is nothing but silica. You'll also notice that as we go from felsic igneous rocks at this end to ultramafic igneous rocks at this end, the volatile content, that's the dissolved gas content, decreases as we go from felsic to ultramafic. Now, this means that felsic and intermediate magmas have lots of dissolved gas in them, and therefore they are prone to forming volcanoes, which are prone to having explosive eruptions. In contrast, mafic and ultramafic magmas would form volcanoes that would be, on the whole, relatively unexplosive. Now, I know we've recently seen pictures, well, not recently, but you've probably seen pictures in the past of volcanoes erupting on Hawaii, and you've seen these lava fountains with, jets of lava shooting several, tens of feet into the air. I've got to be honest, by geologic standards, that's quite a gentle eruption. Okay? So even though these lava fountains might look quite impressive, they are, in fact, by geologic standards, not really that much. So, as we go from felsic to ultramafic, we also have a steady increase in viscosity. So the lava essentially, if it's felsic, has a very, very high viscosity. It behaves like molasses that you've left in the fridge for a couple of weeks. In contrast, an ultramafic magma has a very, very low viscosity. It would flow more like water. And the viscosity is a direct reflection of the amount of silica and the temperature. The higher the temperature, the lower the viscosity. Essentially, the higher the amount of silica, the higher the viscosity. So felsic magmas are low temperature and high silicon, so they have a very, very high viscosity. In contrast, ultramafic magmas are very high temperature, very, very low silica, and as such, they are low viscosity. And then, of course, as we've discussed, we have the general composition. So ultramafic magmas are very, very rich in magnesium and iron especially. Mafic magmas are very, very rich in calcium, magnesium, and iron. Intermediate magmas are rich in silicon, sodium, potassium, calcium, and aluminum. And felsic magmas are rich in silicon, sodium, and potassium. And of course, that will directly affect what minerals form when these 4 types of magma cool. So we've already touched on this, but let's just fire through these once again. So common plutonic igneous rocks, these are the rocks that form underground. Felsic magmas give you a granite. Intermediate magmas give you a diorite, or also referred to as a granodiorite, depending on slightly different compositions. Mafic magmas give you a gabbro, and ultramafic magmas will give you what we refer to as a peridotite. Now, to be clear, the term peridotite is what we refer to as a bucket term. So there's actually several subclasses of rock which make up the peridotite group, but we refer to them all as peridotite, and this photograph here shows you quite nicely. So on this side we have a xenolith of lertzolite, and you can see from the green colour, lertzolite consists mostly of olivine with a few dark green pyroxenes mixed in there as well. Over here on the other hand we have a rock called a pyroxenite. As the name suggests, the rock is mostly made up of pyroxene with a little bit of olivine mixed in there. Now, both of these types of rock, despite the fact they are, in terms of their minerals, extremely different, they are both classified as peridotite. So just be aware that peridotite is a bucket term, and it's not really a name for a type of rock in general. We would tend to try and classify the rock a little bit better, but we're not going to be worrying about that as part of this course. So what about the extrusive rocks? Well, extrusive rocks come in two forms. There's the lavas, which essentially is what we're most familiar with, because let's face it, when we see pictures of erupting volcanoes, the news programs like to show pictures of lava rolling across the surface because it looks pretty. So, as we've already discussed, lavas are made of magmas, which come in these four different varieties: felsic, intermediate, mafic, and ultramafic. And when the lavas cool, they will give you these four standard types of rock. Felsic gives you a rhyolite, intermediate gives you an andesite, mafic gives you a basalt, and ultramafic gives you a komatiite. Now, lava becomes darker with increasing concentrations of iron and magnesium minerals. So essentially, as you go from rhyolite to komatiite, the colour of the rocks that are produced by the magma gets darker and darker and darker. We should also note that rapid cooling of felsic and sometimes intermediate magmas can produce obsidian, which is known as volcanic glass. And so if you were to take a piece of volcanic glass of obsidian and you were to melt it down, it would actually have exactly the same composition as a granite or a rhyolite. So we can discuss in lab class, why it has this dark colour, but we're not going to get into that now. Now, the other kind of extrusive igneous rock you can get are the pyroclastic or the volcanoclastic igneous rocks. Now, these are formed during the explosive portion of an eruption. Now, the likelihood of an eruption being explosive is directly related to the amount of volatile gases, and especially water, dissolved in the magma. So felsic and intermediate magmas have lots and lots of volatiles dissolved in the magma. So that means that as the magma moves to the surface, those gases can come out of solution in the magma and they can form gas bubbles, and gas bubbles expand rapidly, and that can cause an explosion. So felsic and intermediate magmas are associated with explosive volcanism, and therefore you are very likely to have pyroclastic and volcanoclastic rocks associated with them. In contrast, mafic and ultramafic magmas have a much lower volatile content, the eruptions are nowhere near as explosive, and as such the quantities of pyroclastic and volcanoclastic rocks associated with them are a lot lower. So common extrusive igneous rocks form from lava. Felsic magmas give you a rhyolite, intermediate magmas give you an andesite, mafic magmas give you a basalt, and ultramafic magmas give you a komatiite. Now, just to be clear, komatiites don't actually form anymore. So the last komatiite was erupted probably somewhere in the region of around 1 billion years ago. And that's simply because you can't produce ultramafic magmas in a large enough volume anymore to actually produce enough of them to make it to the surface. Because as I said, approximately 90% of all the magma produced will never make it to the surface. So in order to have enough magma to make it to the surface to be erupted, you need to produce very, very large volumes. And in the case of komatiites, we can no longer produce very, very large quantities of ultramafic magma because the Earth's mantle is steadily getting cooler. And that means there's no longer the temperatures down the Earth's mantle to actually form these komatiitic magmas. Okay, so how do we actually classify extrusive igneous rocks? Well, as you can see, when you look at them, the vast majority of these samples is extremely fine-grained, so you can't actually see the minerals without a microscope. Now, unfortunately, we do not have huge quantities of microscopes to work with, so we have to classify these rocks based on something we can see. And what we can often see are the phenocrysts. You can see some phenocrysts here, and you can see some phenocrysts very clearly here. So in the case of komatiites, we don't really worry about those because they're no longer formed. And most komatiites that are around now are not fresh. They've been altered. So what you can see this particular komatiite here. Initially, when it formed, it probably would have been pretty close to jet black in colour. However, you can see now it has this kind of grey-green colour to it, and that's because the rock has been altered. So, we're not looking at the original rock there. So when it comes to classifying extrusive igneous rocks that form from lavas, we only really worry about rhyolites, andesites, and basalts, because they're still forming now. So what we do is we look at the phenocrysts associated with the samples. So in the case of a basalt, we would look for plagioclase phenocrysts, olivine phenocrysts, and pyroxene phenocrysts. They would tend to be relatively common. In the case of andesites, we would keep an eye out for plagioclase phenocrysts. They tend to be very, very common, and also hornblende phenocrysts. You'll note that in the case of basalts and rhyolites, amphibole phenocrysts are relatively rare. Hornblende is an amphibole, by the way. So if you see amphibole phenocrysts, hornblende phenocrysts, chances are you are looking at an andesite. In the case of basalt, you'll notice that olivine phenocrysts are frequently present. Often present, I do apologise. Whereas in the case of andesites and rhyolites, they're not there at all. In the case of rhyolites, we can see that plagioclase phenocrysts are often present, possibly maybe a little bit of hornblende. Biotite is often present, potassium feldspar is often present as phenocryst, and quartz is often present as phenocrysts. So you can see that each of these three different types of rocks have different phenocrysts associated with them. So by simply looking at the phenocrysts, you can make an educated guess about what type of extrusive igneous rock you are looking at. And on the whole, it's a relatively reliable technique. You will also use the rock's colour as well to help you gauge what type of rock you're looking at. Of course, rhyolite, because it's dominated by these light-coloured minerals, will have quite a light colour. Basalt, on the other hand, because it's dominated by darker coloured minerals, will tend to have quite a dark colour. And andesite will sit somewhere in between. So if we go back to the previous slide, you can see light colour, dark colour, somewhere in between. So what about pyroclastic rocks? Pyroclastic rocks can also be referred to as volcaniclastic rocks. So pyroclastic rocks are formed during the explosive portion of an eruption. So they're most commonly formed during rhyolitic and andesitic eruptions because those two types of lava have the greatest amount of dissolved gas in them. So they're classified based on the size of the rock fragments that you actually get in the rock. So if your rock fragments are less than 2 millimeters, they're referred to as ash. If they're between 2 and 64 millimeters, they're referred to as lapilli. And if they're if they're in excess of 64 millimeters, they're referred to as blocks. So a block can be anything from, a 6.5 centimeter size little cube of rock, all the way up to giant boulders. So, block is a pretty broad term. So pyroclastic rocks are classified based on the modal abundance, the amount of these three types of particle that you get within the rock. So when an andesitic or rhyolitic volcano erupt, they tend to erupt in a very explosive fashion. So here we go, this is a classic example. This is Mount St. Helens. So Mount St. Helens erupted in, I believe it was 1982. So this is the before shot of Mount St. Helens. This is facing the same side we're seeing in both pictures. We can see, standard looking volcano, very, very big. It's a composite cone volcano, so it's got very steep sides and it's very, very tall. And we can see after the eruption, well, we can quite clearly see we're missing about a quarter of the volcano. It's literally been blasted away. And a lot of that material that gets blasted away will get turned into ash lapilli and blocks. Here we can see the same thing. This is Mount Pinatubo here. This is in the Philippines. This is 1990. We can quite clearly see all of this material. This is going to be mostly ash and dust getting blasted up into the atmosphere when the volcano explodes, forming what we refer to as this Pelion eruption column. Now, of course, I'm sure you remember, you probably know this saying, what goes up must also come down. And so this Pelion eruption column will go flying up into the atmosphere, but eventually it will lose velocity, and it will collapse, and it will come back towards the Earth's surface, and it will then roll down the side of the volcano. And when it rolls down the side of the volcano, it forms one of these. This is referred to as a pyroclastic flow. And so this is the thing that destroyed the city of Pompeii. So you have to remember that these pyroclastic flows is a mixture of ash and dust and superheated gas. So the temperature of this pyroclastic flow here could be anywhere between about 700 and typically about 900 Celsius. They can be very, very high temperature because there's a lot of very, very hot gas in this pyroclastic flow. So ash Pelion blocks can be formed during an explosive eruption by destroying pre-existing rocks. That's pretty logical. However, they can also be formed when blobs of lava get thrown into the air where they cool and solidify. So if you imagine in this Pelion column here, this Pelion column here has a temperature of somewhere in the region of, once again, 750 to about 900 Celsius. So it's actually very, very hot inside this Pelion column. So that means when little pieces of ash get thrown up into the air, when little pieces of magma get thrown up into the air, they get launched up, and they are in this very, very hot environment. So they never actually fully cool when they're in the column. They behave as kind of a plastic, think like silly putty. They're kind of semi-solid. And so these ash particles will go up, and they will obviously fall back down when the column starts collapsing. So they will end up forming particles that look like this. This is a very, very high level magnification image of a particle of ash, and this is what ash actually looks like if you hold it in your hands. And it's just made by tiny little blobs of lava that get thrown up into the air as the volcanic eruption occurs. Now, some of these little blobs of lava will stick together and they'll form these particles here. These are what we refer to as lapilli. These are what we call accretionary lapilli because they're made up of lots of little particles of ash all stuck together. So when you get larger blobs of lava thrown into the air, well, obviously, depending on what happens to them, they can cool in different ways. So it's how well cooled is the lava and how is it moving through the air. That will combine to essentially affect the shape of the particle you end up with. And of course, the particles that these blobs of magma produce are known to us as volcanic bombs. So, as you can see here, we have 5 different types of volcanic bomb. We have number 1, a ribbon bomb, number 2, a spherical bomb, number 3, a bread crust bomb, number 4, a fusiform bomb, and number 5, a cowpat bomb. So in the case of a ribbon bomb, essentially the blob of magma, a blob of lava that's gotten thrown up into the air, essentially begins to rotate as it moves through the air, and it begins to get drawn out into a ribbon. So it forms a spiral, essentially. And so you end up forming these very, very distinct ribbon bombs. In the case of a spherical bomb, also referred to as a cannonball bomb, the blob of lava goes up into the air, it forms an approximately spherical shape, and it cools down in the air and it hits the ground pretty much solid. Now, in the case of a bread crust bomb, exactly the same thing happens. A blob of lava gets thrown up into the air, it forms an approximately spherical shape, and the exterior of this blob of lava cools down, forming a crispy crust. The interior, on the other hand, remains liquid. So when the bomb hits the ground, the crispy crust shatters and breaks, and the liquid interior seeps out along the cracks where it then solidifies. And so you end up with this kind of bread crust-like appearance, hence the term bread crust bomb. Now, in the case of a fusiform bomb, essentially you have this blob of lava that gets thrown up into the air, and as it gets thrown up into the air, it begins to spiral. And you end up forming this shape a bit like a football. Gets drawn out, and so you end up with pointed tips at the rear and the front, but the main body remains approximately spherical in size. And then finally, you have bombs that form from lava that remains completely liquid as it goes up, never solidifies, so when it hits the ground, it just goes splat, and you end up with this rather distinctive type of bomb, which is referred to as a cowpie or cowpat bomb. So when we classify volcanoclastic rocks or pyroclastic rocks, we classify them using this system here. Up here we have ash, so this is 100% ash here, 0% ash down here. We have lapilli, 100% lapilli here, 0% lapilli along this line here. And we have blocks, 100% blocks over here, 0% blocks along here. And I'm going to be honest, most pyroclastic rocks tend to fall between the ash and the lapilli lines because they tend to have very few blocks within them. And so most Pyroclastic rocks will tend to be either tuffs, which are ash-dominated rocks, lapilli stones, which are lapilli-dominated rocks, or lapilli tuffs, which are a mixture of the two. That tends to be the vast majority of rocks. Only very rarely do you get pyroclastic rocks that are dominated by blocks. To be clear, tuff is not pumice. They are actually different types of rock altogether. So let's think about the... Well, actually, do you know what? Let's not think about the volatiles right now. Let's take another break. So, once again, stop the presentation, get up, have a walk around, go and get a glass of water, come back in a couple of minutes when you've got a clearer head, and we'll start again. Okay, everybody. So now we're going to think about the volatiles that are dissolved within the lava. So as mentioned, lavas become more volatile rich as the SiO2, the silica content, increases. So felsic and intermediate magmas, lavas which have a very high silica content also have lots of volatiles dissolved in them. So that means they are prone to being that means they're prone to causing explosive eruptions. So of course, as the lava moves from deep in the crust towards the Earth's surface, the ambient pressure decreases, and this allows any gas dissolved in the lava to begin to exit solution. Of course, the classic example of that is a bottle of any kind of soft drink you can think of, let's say Coke. Of course, when the cap is on the bottle of Coke, the pressure inside the bottle is very, very high, so the carbon dioxide remains in solution. However, as soon as you open the cap, the pressure inside the bottle drops, and the carbon dioxide that is dissolved within the Coke exits solution and forms bubbles. And that's exactly the same process. Now, in the case of volcanoes, sometimes it's not that straightforward. So as the lava moves up the pipework inside the volcano, tries to get towards the surface, it will very often get stuck behind a blockage. It's sometimes referred to as a bottleneck or a cork. And so what happens is the lava gets stuck behind this blockage, and more lava is building up behind this blockage, and so the pressure starts getting higher and higher and higher. And so this means that the volatiles which are in the lava will go back into solution. And so what happens is the pressure keeps, the amount of lava keeps building up behind this blockage, the pressure keeps getting higher and higher and higher, and eventually the pressure will get so high that the rock surrounding it will fail, and when the rock fails, the pressure will drop very, very quickly, and then all of that gas that's held in solution within the lava will also come out very, very quickly, and that means there's a very quick increase in volume because all the gas comes out in one go. The volume of the lava increases very, very quickly at one time, and essentially when you have this very, very large volume increase, you have an explosion. So in the case of the Mount St. Helens eruption, there was a blockage, so the lava was trying to make its way towards the surface, and it got stuck behind a blockage at the top. And so the pressure built up and up and up as more and more lava got stuck behind this blockage, until eventually there was a landslide on the north face of Mount St. Helens, and that landslide caused the pressure to decrease, the pressure that the lava was being exposed to decrease. All of a sudden, the dissolved gas came out of solution rapidly, and the sudden increase in volume caused an explosion that took out about 1/4 of the volcano. So these volatiles are extremely important in terms of the style of eruption we get. Now, if you have a little bubble of gas that gets trapped inside your lava as it's cooling, it forms a approximately spherical to elliptical void, which we refer to as a vesicle. I'm sure you remember that term. And there are two types of rocks in particular that are extremely highly vesicular. They are pumice and scoria. And you can see from both these pictures, they are absolutely stuffed with these vesicles. So let's look at pumice to start with. So pumice is light in colour. It forms from felsic to intermediate lavas. The lavas themselves have a very high viscosity. Now that means the gas bubbles, because they're trying to move through a very viscous liquid, can't often join up. So that means the vesicles that form tend to be very, very small. The lava itself tends to have a very high volatile content, so you'll form lots of these gas bubbles. So there's lots and lots of vesicles in this rock. And so because of this high viscosity and the high volatile content, you get lots and lots of very, very small vesicles. And that means pumice is actually more vesicle than rock. And so pumice will actually float on water. In the case of scoria, it's much darker in colour. When it begins to weather, it will go rust red in colour. It's formed from intermediate to mafic lavas. It has an intermediate to low viscosity. Now that means these gas bubbles can join together, so you tend to get larger vesicles forming. The lava itself also has a lower volatile content. That means the number of vesicles you form will also be lower. And so this means your rock ends up containing numerous moderate to large vesicles, which means scoria is more rock than vesicle, so if you put scoria in water, it will sink. Now, in the case of both these rocks here, they don't actually contain crystals. What happens is when the lava is getting erupted at the surface and all this gas is coming out very, very quickly, forming all these vesicles, the process of forming vesicles is actually a endothermic process. It uses up heat energy to actually make the vesicles. And so the more vesicles you form, the more heat energy gets used up from the lava. So if you imagine a lava suddenly releasing all this gas in one go, it causes the lava to cool down very, very quickly because lots of energy is being used to make gas bubbles. And so pumice and scoria, which is absolutely stuffed with these vesicles, which were gas bubbles, essentially the lava that forms them cools down very, very quickly. And so that means the lava never really has time to form crystals. So both pumice and scoria are mostly made up from volcanic glass. In the case of pumice, it's a felsic to intermediate volcanic glass. In the case of scoria, it's a intermediate to mafic volcanic glass. So the final thing we're going to think about is how are magmas actually generated. So to create a magma, you obviously have to melt a rock. So in order to actually create enough magma so that it can migrate out of the rock, you need to melt approximately 20% of the rock. Now, why is this? Did I put a picture in? No, of course didn't. That would have been helpful, but I didn't. So why do you have to melt 20%? Well, most of the time when a rock starts melting, the first magma droplets form along the contacts between crystals. Now, this means that you get all these little blobs of magma that start forming on the contacts between the crystals. However, they're all isolated from one another. It's only when you've melted about 20% of the rock do you have a large enough volume of these little droplets that they can begin to join together and they can begin to form a network along which the magma can exit the rock. So this magic 20% number is all important. So rocks are composed of minerals, and of course each mineral has its own liquidus and solidus temperature. So the rock will begin to melt once the temperature exceeds the solidus of the lowest temperature mineral. So you need to remember the position of the liquidus and solidus change with pressure. The higher the pressure, the higher the temperature required to melt the rock. So this phase diagram here is for olivine. And so what have we got going on? So here's the olivine composition, and here's the temperature. And what you'll notice is, so here we have the solidus, that's essentially the melting line for solid crystals of olivine. So if I have a crystal of olivine that's 40% phthalate, 60% phosphorite, I come up here, I'm going to require a temperature of somewhere in the region of around 1,500 Celsius to melt it. In the case of about 20% phthalate, 80% phosphorite, I'm going to require a temperature of somewhere in the region of around 1,700 Celsius to melt it. So those are the kinds of temperatures I have to reach if I want to melt olivine. For each mineral, this phase diagram will be different, and the temperatures obviously will be different as well. So some minerals like muscovite, or muscovite in particular, has quite a low melting temperature, so it won't take much heat energy to melt it at all. Most of the time, if you ever see a phase diagram like this, it's based on a pressure of 1 atmosphere. Now, as I said, as the pressure gets up, as the pressure increases, this solidus is going to move upwards, and so the temperature required to actually melt solid olivine is going to get higher and higher and higher as the pressure increases. Okay, so rocks will melt in response to changes in 3 variables: temperature, pressure, and the amount of volatile substances. So the first type of melting you can get is thermal melting, and that's when you essentially just heat a rock up. So the solidus for mantle rocks, that's therefore of course referred to as peridotite, is on the whole above the ambient temperature, so no melting occurs. The mantle is solid, and that's because pressure is high, essentially is in control, so the minerals in the rocks can't melt. However, if mantle convection brings up very, very hot material from the very deep mantle, that very, very hot material from the deep mantle can induce melting in the upper mantle rocks, because it's just heating them up very, very quickly. In fact, heating them up so quickly that the high pressure is not sufficient to stop the rock from melting. So this can also happen when magma intrudes the Earth's crust. So if you imagine you get a mafic magma with a temperature of 1200 Celsius intruding the Earth's crust, and the Earth's crust is made from granite. Granite has a melting point of around 750 to 800 Celsius. Well, what's going to happen? Answer is the granite's obviously going to melt because of the heat coming off the mafic magma. So melting of deeply buried felsic material at the base of the crust can be induced this way. So here's the situation. So this is the geotherm. This is the change in temperature as you go deeper into the Earth. So here we have depth and here we have temperature. So you can see as you go further and further into the Earth, the temperature gets higher and higher and higher. Not really a huge shock there. So here we have the melting curve for dry peridotite. That's the stuff that makes up the mantle. So you'll notice the melting curve, the temperature required to melt dry peridotite is nowhere near the geotherm, and as such, the peridotite will not melt. Here we have the melting curve for basalt, once again, nowhere near the geotherm, so the basalt will not melt. Same thing over here. This is the geotherm for granite, once again, nowhere near, so it's the melting curve for granite, once again, nowhere near the geotherm, so the granite will not melt. So what you need to do is you need to increase the temperature. So if you put a very, very hot ball of magma into the crust, you increase the geotherm, you make the geotherm essentially steepen up, and you are, to all intents and purposes, pushing the geotherm to the right. And if you push the geotherm far enough in the right, it can melt granite, it can melt basalt, and if you make it go far enough, it can even melt peridotite. So in the case of thermal melting, you're increasing the temperature and you're pushing this geotherm off to the right until it hits the melting curves for these different types of rock. And once it hits the melting curve, the rocks will begin melting. So then we have changes in pressure. So increased pressure reduces the likelihood of melting, as we've discussed on a few occasions. So what happens is if your rock is very, very hot, but the pressure starts decreasing quite quickly, well, that can lead to what we refer to as decompressional melting. So this can occur in one of a few ways. So if you have a hot mantle rock that's rising very, very quickly, so let's say it's this mantle rock is coming from very, very deep in the mantle, so it's under very, very high pressures and temperatures, and it rises up through the mantle very, very quickly. It remains at a very high temperature, but as it rises up through the mantle, the pressure starts getting lower and lower and lower. That can allow the rock to start to melt. Now, the most common place we get decompressional melting is under spreading ridges, or mid-ocean ridges, you know them, are divergent plate boundaries. So at spreading ridges, the thickness of the oceanic crust is typically a lot less. So in the case of oceanic crust, it typically has a thickness of about 7 kilometers for the oceanic crust, and typically you have about, give or take a little bit, about 10 kilometers of mantle rock stuck onto the bottom of the oceanic crust. So you've got something in the region of about 15 to 20 kilometers of rock in normal average oceanic crust. And so that means the mantle rocks underneath that oceanic crust are going to be under, the amount of pressure exerted on them by having 20 kilometers of rock pushing down on them. Now, when we move towards a spreading ridge, the thickness of the oceanic crust decreases from about 20 kilometers to somewhere in the region of about 2 or 3 kilometers. And so that means the mantle rocks underneath a spreading ridge are under considerably lower pressure. However, they're at the same temperature, so the rocks that are under 20 kilometers of crust and the rocks that are under 3 kilometers of crust, they're at exactly the same temperature. They're both very, very hot. And so the rocks underneath the spreading ridge are at very, very high temperatures, but lower pressures, and as such, they begin to melt. So what's happening is, in the case of the changes in pressure, the geotherm is being pushed upwards. Okay, so as the pressure drops, the geotherm comes up, and once again, as the geotherm rises, it can hit the melting curve for granite, it can hit the melting curve for basalt, and it can hit the melting curve for peridotite. So depending on how far the pressure decreases, you can make it either melt granite, basalt, or peridotite. So once again, it's relatively simple. All you're doing is you're just changing the pressure, and that's causing, in this case, the geotherm to rise up. The final type of melting is hydration melting. So that's essentially the process of adding water. So by adding water or carbon dioxide to very deep crustal rocks, basalts or mantle peridotites, you can induce melting. So why do they actually induce melting? Well, the volatiles can react with the minerals in the rock, especially anhydrous or water-free minerals, or they can actually enter the crystal lattice. So okay, let's start with the latter of those. So if you imagine, you have a whole group of people all holding hands, and then you have a group of people just pushing in between them, causing people who are holding hands to essentially lose grip of one another. That's essentially what happens when the water literally forces its way into the crystal lattice. So the water will push its way into the crystal lattice, and it will disrupt the bonding inside the minerals. It will make the minerals unstable, and they will begin to melt. The other possibility is that the rock that you're dealing with contains a lot of these anhydrous, water-free minerals, and then you expose them to water. Well, what happens? The anhydrous minerals, like olivine, will very, very quickly react with the water. So when olivine meets water, it forms a mineral called serpentinite. Now, olivine is stable at very, very high temperatures and pressures. Serpentinite is not. So when you turn olivine into serpentinite, the serpentinite suddenly realizes the temperature and pressure is too high, and it begins to melt. So there are two ways that you can make rocks melt due to adding water. The most common way is simply due to this reaction of anhydrous minerals with the water, producing new minerals which are unstable at the very, very high temperatures and pressures. Now, hydration melting is most commonly associated with subduction, where the subducting piece of oceanic crust manages to pull large quantities of water very, very deep into the mantle, and typically that water will come out of the descending oceanic crust and the minerals in that oceanic crust at a depth of somewhere between 100 and 150 kilometers down. And when that happens, that water gets released, it goes up into the mantle above the piece of descending oceanic crust, and it causes that mantle to begin to melt, and that mantle melting will produce a mafic magma. So what we're doing in the case of hydration melting, we're taking the geotherm and we are doing nothing to it whatsoever. The geotherm in this case is stationary. What we're doing in this case is by adding water, we are taking the melting curve for material, in this case basalt, and we are driving it to the left until it intersects the melting curve of the geotherm, at which point it starts to melt. Over here we have the melting curve for granite. You can see this is dry granite here. Add a bit of water to granite. You drive the melting curve for granite once again off to the left. So by adding the water, you are essentially reducing the melting point of the minerals in the rock. So this is the grand model. So typically in a normal situation, your geotherm never comes near your solidus, and so no melting occurs. So in the case of mid-ocean ridges, we have this normally very, very thick oceanic crust here is much, much thinner here. So it's normally about 20 kilometers here. So the oceanic crust is normally about 20 kilometers. By the time you make it to here, it's only somewhere in the region of about 2 or 3 kilometers. So the mantle rocks here, which are at 1,200 Celsius, but under a lot of pressure, will not melt. Mantle rocks over here are at 1,200 Celsius, but under a much lower pressure. Well, in that situation, the geotherm gets driven, it gets pushed upwards until it intersects the solidus, and so it causes the rock to begin to melt. So the rocks underneath spreading ridges will melt. It's mantle rocks melting under spreading ridges, and so that's going to create mafic magmas. In the case of thermal melting, this is where we have a mantle plume coming up from the deep mantle. It gets stuck at the base of the oceanic crust. It begins to heat up and melt the oceanic crust, and it produces magma that rises to the surface, feeding volcanoes. So in this case, you are melting both mantle rocks and crustal rocks, so you're going to end up with magmas that have a composition somewhere in the region of a mafic to intermediate composition. So in this case, here's the geotherm. By increasing the temperature, we are driving the geotherm to the right until it intersects the solidus, at which point the rock will start melting. And then over here we have hydration melting. So this is our piece of oceanic crust. It descends down into the mantle to about 150 kilometers. That's the magic number. At which point the water in the minerals within the oceanic crust, essentially those minerals release the water. The water goes into the overlying mantle rocks, causing them to melt. That produces a basaltic magma. That basaltic magma rises up. It gets stuck at the base of the crust, the continental crust. When it gets stuck at the base of the continental crust, it starts melting the continental crust, which is made mostly of granite. So what we're actually getting is a melt that is felsic in composition because it's being formed from melting granite. So then that magma formed from melting granite then rises to the surface where it feeds volcanoes. So we have initially hydration melting here, which then causes thermal melting at the base of the crust, and that thermal melting essentially produces a magma that rises to the surface and feeds volcanoes at the surface. So that's the grand model for how magma is produced. Okay, so once again, get up, stop the video for a few minutes, walk around, get yourself a glass of water, and come back in a little while. Okay, so now we're going to spend some time thinking about metamorphic rocks. So metamorphic rocks are the result of mineralogical changes caused by increasing or decreasing pressure and temperature. At no point does the rock melt, and you'll notice there's little asterisks here. So the vast majority of metamorphic rocks are formed through the process, are not formed due to melting. However, there are a couple of occasions where metamorphic rocks do involve a small quantity of melting in order to form them. So it's not a hard and fast rule that a metamorphic rock cannot involve some melting, but the vast majority of metamorphic rocks do not involve any melting. So metamorphic rocks are classified by their mineral assemblage and their texture. So the precursor rock that's about to be heated up or exposed to high pressure and temperatures is referred to as a protolith. So that's the starting material. So the protolith will be heated up and the minerals within the protolith will change to give you a new rock, a metamorphic rock. So the basic classification for metamorphic rocks is based on the metamorphism of a basalt protolith. So this means that essentially when we look at the minerals that we're forming and we're talking about the minerals in the general classification, we are just talking about what happens when you metamorphose a basalt. So zones are defined based on the presence of one or more distinct minerals, and these minerals are referred to as index minerals. So the presence of some common minerals in metamorphic rocks allows us to very quickly work out what the likely pressures and temperatures were to which that rock was exposed. So these pressure and temperature ranges that are defined using the index minerals are used to draw essentially boundaries, and they're used to define regions of pressure and temperature which we define as facies. So metamorphic facies is a pressure and temperature range within which certain minerals are stable. So once the index minerals for each facies break down to form new minerals, you have obviously left that facies. The mineral assemblage is, unsurprisingly, a reflection of the protolith. So typically when we talk about metamorphic rocks, we only tend to talk about the metamorphism of basalts and mudstones. The reason for that is when you metamorphose either basalts or mudstones, you tend to get distinct changes in mineralogy. In contrast, when you metamorphose something like a sandstone or a limestone or a granite, the changes in mineralogy you get are relatively minimal. So those types of rocks essentially don't really metamorphose particularly well, so we don't see these big changes in mineralogy, and so we can't really use them to gauge pressure and temperature. We need the minerals to change in order for us to try and work out what the pressure and temperature the rock was exposed to was. So what we can do is, even if the protolith isn't a basalt, we can use the pressure and temperature limits for the facies, which were defined by a basalt, to essentially describe the temperature and pressure at which to which a rock has been exposed. So this is the diagram here. So each of these zones is defined using the pressure and temperature zones of a granite. So of a basalt. So here we go. So if I was to metamorphose a basalt to between about 275 and about 475 Celsius, and about 1 kilobar pressure and 8 kilobars pressure, I would fall in this zone here, which is called the green schist facies. Now in this particular zone here, there are 3 minerals that are stable: chlorite, epidote, and actinolite. And if I have those three minerals together in a rock at the same time, I know I must be in the green schist fascies field. Now, as soon as the pressure and temperature begins to increase, actinolite breaks down to give me hornblende, which is the type of amphibole, and chlorite and epidote will break down to give me the mineral plagioclase feldspar. So as soon as the temperature begins to increase, those three minerals become unstable, and eventually, when I cross this line here, actinolite, epidote, and chlorite disappear, and they are replaced by hornblende and plagioclase feldspar. Once that happens, I've left the green schist fascies field, and I've entered the amphibolite fascies field. So you can see for each of these fascies, you can see there's essentially a minimum pressure, maximum pressure, minimum temperature, maximum temperature. And so that means what we do is any rock that achieves these pressures and temperatures will be defined as having met, having achieved that level of fascies. So if I was to take a mudstone and I was to take it to 400 Celsius and 4 kilobars pressure, so the point's going to be around here, even though it's a mudstone that's being metamorphosed, so remember this diagram is based on a basalt, but even though it's a mudstone that's being metamorphosed, my point's going to be here, I would still say that mudstone has reached green schist fascies grade. So although this diagram, as I say, is based on a basalt, these fields are used to describe the temperatures and pressures that all metamorphic rocks meet. So essentially, I can say, oh, my granite, was metamorphosed to amphibolite fascies, or my basalt was, metamorphosed to eclogite fascies, or my limestone was metamorphosed to blue schist fascies, depending on the pressure and temperature the rock was exposed to. So, as I was saying, when it really comes down to metamorphism, we tend to focus on two groups of rocks, the basalts and the mudstones. So the mudstones also contain the siltstones and the claystones. And so that's because these are the only types of rock, when they metamorphose, you get distinct changes in metamorphic minerals as the pressure and temperature increases. So in the case of basalts, you can see here we have low-grade metamorphism, so that's green schist fascies. There we go. Then we have intermediate grade metamorphism, amphibolite fascies, there. And high grade metamorphism, granulite fascies, there. So as we go from low grade to high grade metamorphism, you can see the types of minerals we have change. Eventually chlorite, epidote become unstable. They're replaced by amphibole, garnet and pyroxene as the temperature and pressure increases. So we can look for these indicator minerals, these index minerals, and that will help us to work out what the pressure and temperature was that our rock was exposed to. And we get the same thing for mudstones. So low grade, intermediate grade, high grade. And so as we increase the pressure and temperature, so low-grade rocks will have chlorite and muscovite and biotite, maybe a bit of quartz and feldspar. As you move to intermediate grade, the chlorite becomes unstable. Eventually, the muscovite will also become unstable, and they'll be replaced by garnet, staurolite, and kyanite. And by the time we make it into high-grade mudstones, essentially all of these phases, well, biotite persists for a little while, so does garnet, but essentially once you make it past this boundary here, sillimanite is the dominant index mineral. So, as you can quite clearly see, even though we're metamorphosing a rock that isn't a basalt, we still use the fascies names to define the general pressure and temperature range to which the rock has been exposed. So, when we discuss metamorphism, we typically discuss three distinct pathways along which a rock can be metamorphosed. There is contact metamorphism, regional metamorphism, and subduction metamorphism. So contact metamorphism takes what's referred to as a low pressure, high temperature path. So as you can see, low pressure down here and temperature increases, so it follows this red line here. And it will give us a group of rocks which we refer to as the hornfelses, and eventually the very high grade rocks which we refer to as the sandanites. Regional metamorphism is often referred to as high pressure, high temperature metamorphism, and it will follow this path here marked out in green. And it will lead us through green schist fascies rocks, through amphibolite fascies rocks, and eventually into granulite fascies rocks. Regional metamorphism is also referred to as Barrovian metamorphism, although that tends to be a more old-fashioned term. And then finally we have subduction metamorphism. That's high pressure, low temperature. So it takes the path marked out by its purple line, and that will lead us through blue schist facies and eclogite facies. So as you can see, as a rock moves along one of these general trends, it can pass through 2 or more facies as as the pressure and temperature gets higher. So we'll see distinct changes in mineralogy as the rock passes from one facies to another. So metamorphism can occur in 2 directions. There is prograde metamorphism, that's when you increase the pressure and temperature, but there is also retrograde metamorphism, that's when the pressure and temperature decreases. So for instance, we can have a rock and we can start to heat it up. It can undergo prograde metamorphism, so it can go through green schist facies, into amphibolite facies, into granulite facies, and then all of a sudden the pressure and temperature begin to drop. Well, when that happens, the rock will begin to go back the other way. It will go from granulite facies back through amphibolite facies back into green schist facies. So metamorphism isn't always about increasing the pressure and temperature, but in the vast majority of cases, that's how we describe it. So regional, I should say, regional and subduction metamorphism essentially form in environments with a moderate to high pressure. Now these moderate to high pressures will cause the minerals in those types of metamorphic rocks to align, producing a fabric. There will be a distinct layering to the metamorphic rock, and this layering is referred to as a foliation. Now contact metamorphism, this path down here, occurs in low pressure environments, so there is no pressure forcing the minerals to align. This means the minerals within contact metamorphic rocks will have random orientations, there will be no layering, and as such the rock is described as unfoliated. Unfoliated rocks can also form in high pressure environments when the pressure is equal in all directions, or if there are no elongate or platy minerals. So number one, if you take a rock and you take it all the way down into the mantle, well, by the time you put that rock in the mantle, the pressure is pretty much equal in all directions. So even though it's a high pressure environment, there's no one dominant direction of pressure, so the minerals can't align themselves. The other thing is that if you have a rock that's made up of crystals that are approximately spherical in shape, well, you can't really align spherical crystals. You can only align crystals if they're platy, like pages in a book, or if they're elongate, like pencils. So if you have the wrong minerals in the rock, you couldn't form a foliation anyway. Alright, so we're going to start with contact metamorphism. So contact metamorphism results from the heating of the country rock around an intrusion. So here's our igneous intrusion. Now, the igneous intrusion in this model has solidified to give us a granite, but of course, once upon a time it would have been liquid, so it would have been a big ball of magma. And if it's a granite, that magma would have been somewhere between 750 and about 850 degrees Celsius in temperature. So obviously, and unsurprisingly, it's going to heat up the rock that it's in contact with. So as you move away from the contact, the temperature is going to get lower. As you move towards the contact, the temperature is going to get higher. And so that means as we move towards the intrusion and the temperature gets higher, the types of metamorphic minerals we see are going to change. Out here we're going to have lower temperature metamorphic minerals, and as we approach the intrusion, the metamorphic minerals are going to get steadily higher and higher grade. Now, as we move from one zone to another, the minerals change. So here we have muscovite and chlorite. They give way to biotite and andalusite. Andalusite and biotite give way to cordierite and sillimanite, and eventually we end up with a hornfels. So we have distinct zones which are based on the index minerals that are present, and these distinct zones are referred to as aureoles. And so as you head towards the intrusion, the aureoles, the metamorphic grade of the aureoles will become higher, because the temperature is increasing. So as the pressure is low, no metamorphic fabric is formed. And these fabric-free contact metamorphic rocks are referred to as hornfelses, and this gives you some idea. The vast majority of contact metamorphic rocks form approximately 5 kilometers below the Earth's surface, where the pressure is very, very low. Okay? Now, in the case of intrusions that are much, much deeper, well, in that case, you don't get contact metamorphism, because although this magma here might be 750 Celsius, the rocks that are surrounding the intrusion are also 750 Celsius. So essentially, it can't cause contact metamorphism. Rocks can only be contact metamorphosed if they are of a lower temperature than the intrusion. So hornfelses are split into essentially 4 distinct groups, and we can see them here on this diagram. And so we have increasing temperature this way. Note the pressure stays very, very low at all times. That's because we're in the top 5 kilometers of the crust, so the pressure remains relatively low, geologically speaking. So we have albite epidote hornfels, is the lowest temperature. Then we have hornblende hornfels, which is the intermediate, pyroxene hornfels, higher temperature still, and sandonite, which is the highest temperature of contact metamorphic rocks. Now, as I've discussed, these 4 facies are based on the metamorphism of a basalt. You can also see here, you could get the metamorphism of mudstone. So in this case we have a shale, in this case we have a sandy shale. They will also produce distinct minerals, and we can use those distinct minerals to tell us which way, whether the temperature is getting higher or lower, just like we could using the minerals we see for metamorphizing a basalt. However, look up here, limestone and sandstone. When you metamorphose those 2 rocks, you get very few mineralogical changes. So here's a limestone. You metamorphose a limestone changes into a marble. The only difference is that as you head towards the intrusion, the marble is going to get coarser and coarser grained. The crystals are going to get bigger and bigger. So as you head towards the intrusion, the number of crystals decreases, but the size of the crystals increases. The same goes for the sandstone. As you start off with sandstone, as you metamorphose a sandstone, you just get a rock called a quartzite. You can't really do much with a sandstone. A sandstone just consists mostly of quartz and feldspar. Those are 2 very stable minerals, so heat them up, they're just going to sit there. Same with the limestone, that's made up of the mineral calcite. Once again, it's a very stable mineral. You heat up calcite, it's just going to sit there. So all that happens when you metamorphose a limestone and a sandstone is you just decrease the number of the total number of crystals. That means the crystals that remain get larger. So you end up with fewer, larger crystals. And so your limestone will turn into a coarse-grained marble, and your sandstone will turn into a coarse-grained quartzite. And that's it. And that's why we really focus on these muddy rocks and these basaltic rocks, because those are the only types of rocks that give us these nice changes in mineralogy. Alright, so we've done another 20 minutes, so let's stop for a quick break. So once again, pause the video, have a quick walk around, get yourself a glass of water, and come back in a couple of minutes. Okay, so regional and subduction metamorphism. Well, it's caused by the large-scale action of heat and pressure as 2 massive pieces of crust bang into each other. So regional metamorphism essentially occurs where you have mountain ranges. So where you have convergent plate boundaries. That can either be in the form of subduction zones, like the west coast of South America or the Alps, or it can be in the case of continent-continent collisions like the Himalayas. So essentially what you have are 2 pieces of crust smashing into each other, and that's going to produce very, very high temperatures and very, very high pressures. So what we're going to notice is we're going to end up with a mountain range. Now this diagram here is a little bit crude, but it gives you the basic idea. So here's our mountain range caused by the collision of these 2 pieces of crust. So we have a subducting piece of oceanic crust here, and a piece of continental crust over here, and the collision between the 2 forms a mountain range. Well, obviously, as you go deeper and deeper into the mountain range, the pressure and temperature increases, and so the facies, the grades of the metamorphic rocks, will also increase as you go deeper and deeper into the mountain range. Relatively straightforward when you think about it. So this diagram here shows you approximately the same thing. Now, in the case of subduction metamorphism, it is intimately related to these mountain building events, these orogenies. So in the case of the mountain building event, that's going to cause regional metamorphism. Now, the piece of subducting oceanic crust, on the other hand, that is going to undergo subduction metamorphism. So it's going to undergo a different type of metamorphism. So we'll explain why that is in a couple of slides' time. So just be aware that the subducting piece of oceanic crust is metamorphosing in a different fashion to the regional metamorphism that takes place here in the continental crust. So regional metamorphism occurs in the orogenic front, which is otherwise known as a mountain range. So so the Andes is the Andean orogenic front essentially. So subduction metamorphism increases with grade and depth. So subduction metamorphism increases the deeper the piece of oceanic crust goes into the mantle. So regional metamorphism increases as you head towards the mountain core. So once again, here's our mountain range. So in this case, let's pretend it's the Himalayas. So over here, let's say we have India, and over here we have Asia, and where the two crash into each other, we end up with the crumple zone, which are the Himalayan mountains. So the deeper we go into the Himalayan mountains, the higher the pressure and temperature gets, and therefore the higher the grade of the metamorphic minerals becomes. So as we go here, we're going to go from low temperature minerals like chlorite up here. So this is a low-grade metamorphic mineral to high-grade metamorphic minerals like sillimanite down here. So as you can see, we're going to form these distinct zones when we get these indicator minerals as the temperature and pressure changes. So we're going to go from chlorite to biotite to garnet to andalusite to sillimanite as the pressure and temperature increases. So by the time you're down here in sillimanite, in the sillimanite aureole, chlorite will not be there. Okay, so as you move from chlorite to biotite, the chlorite disappears and it's replaced by biotite. As you move from biotite to garnet, the biotite disappears, it's replaced by garnet. As you move from garnet to andalusite, the garnet disappears, it's replaced by andalusite. As you move from andalusite to sillimanite, the andalusite disappears and it's replaced by sillimanite. So each of these bands has its own distinct mineralogy, which is a reflection of the pressure and temperature. So here we have a couple of examples of regional metamorphism. So we have the Andes, and we have, now this is actually the Himalayas here, marked out in the dark red, but this is also the plateau behind the Himalayas. So this kind of gives you some idea of the size of the areas of land that can be affected by regional metamorphism. So in the case of contact metamorphism, it just affects what's along the edge of the intrusion. In the case of regional metamorphism, it is affecting an area that covers thousands of square kilometers, hundreds of thousands of square kilometers. So regional metamorphism has a very, very serious effect on the Earth's crust. Now, once the mountain range is eroded away, so once this portion of the mountain range here is gone, well, what's going to happen, the crust is going to naturally just bob up. It's going to bounce up. So, think of it this way. If I'm on a trampoline and one of you decides to get on the trampoline with me and sit on my shoulders, well, obviously I'm going to go deeper into the trampoline, aren't I? Now, as soon as you decide to get off my shoulders, jump off my shoulders, I'm going to bob up. I'm going to bounce up. It's called isostasy. So once we remove these upper portions of the mountain range here, all this crust down here is naturally going to bounce up. And so when it bounces up, what happens is these metamorphic zones that were within the mountain range suddenly get exposed at the surface, going from high-grade metamorphism here in the core to low-grade metamorphism out here at the edge. It's a bit like a jawbreaker. And so what we can do as geologists is we can then come along and we can look for these changes in metamorphism, and that's how we know where there were ancient mountain ranges. So here's a couple of examples. So this is Nova Scotia in Canada. When we look in Nova Scotia, we see here we have this orange zone, that's sillimanite. This blue zone here and here, that's andalusite. We have this lighter blue zone here, that's garnet. We have this biotite zone, which is this kind of minty green colour. And we have this chlorite zone here, which is in this really quite disgusting green colour. So what you see here is this is the high-grade zone, right in the middle of the mountain range here, and we're moving towards the edge of the mountain range as we move this way. So we're starting in the high-grade zone here, and we're moving towards the edge of the mountain range and lower metamorphic grades as we go in this direction and this direction. So this tells us that once upon a time there was a mountain range here, and what we can do is we can then take samples of the rocks here and we can date them, and it will tell us when the mountain range existed. Same thing over here. So this is for the northeastern United States. So we've got Vermont, New Hampshire. Let's see, and you can quite clearly see here, and there's Quebec there, which is Canada. You can see here we are going to go from high-grade metamorphism okay, in reds and oranges, and the metamorphic grade is going to steadily get lower as we head towards the purple. So this area here, these oranges, these reds, that represents the highest grade of metamorphism. Then we have this yellow zone. Then we're going to move out into this green zone along the edge. Then we're going to have this kind of intermediate zone. Now, it's not particularly common, it's just occurring up here. So these two green zones are kind of lumped together, really. Then we have this light blue zone, which is here. And then that gives way to the purple zone, which is here. So essentially what we have is the core of the mountain range here, and metamorphic grades decreasing this direction as we move towards the edge of the mountain range. And so once again, we can take samples of the rock here and we can date when this mountain range existed. So what about subduction metamorphism? So subduction metamorphism is intimately related to regional metamorphism. Subduction metamorphism has to occur when you get a piece of oceanic crust subducting underneath a piece of continental crust. That's going to produce a mountain range, and in that mountain range you're going to have regional metamorphism. Now, in the case of subduction metamorphism, it's considered to be low temperature, high pressure. It's high pressure because you've got two massive pieces of crust banging into each other and grinding past each other. So that's going to produce very, very high pressures. In the case of the low temperatures, on the other hand, the temperature is kept low because you have lots and lots of cold water circulating. And as that cold water circulates around, it helps to pick up heat and it transports it away. A little bit like the heat sink in the back of your refrigerator. Essentially, the circulation of the coolant in the back of your refrigerator helps to take heat away from inside your refrigerator and transports it away, thereby keeping your refrigerator cold. So what we tend to find is the metamorphic rocks we get that form during subduction metamorphism are limited to the subducting piece of oceanic crust. So we typically only get two types of metamorphic rock. Those are blue schists and eclogites. So it's these two types of rock here. So this is the subduction trend. We end up with blue schists and eclogites. Now, in both of these cases, the piece of oceanic crust is basalt, and so the metamorphic rocks we get will be called blue schists and eclogites. They'll have distinct mineralogies. So what you'll notice here are the geotherms. This is 400 Celsius and this is 600 Celsius. Now, you would expect this 400 Celsius line to continue straight across and meet up with the line over here. Same for the 600, expect it to go straight across and meet up with the line over here. That's what you would expect. What you can quite clearly see, though, is here at the subduction zone where the piece of oceanic crust is diving down into the mantle, we can see that these geotherms, these temperature lines, are suppressed quite noticeably. And that's simply because in these regions here, you have lots and lots of water circulating around. So it's picking up heat from down here and it's transporting it up. The water becomes cooler again and it falls back down and you end up with this circulation of water. So essentially you have, I do apologize, got to go back. So you have water being heated up here, it rises, cools down, becomes dense again, and sinks back into the subduction zone. So you end up with this constant circulation of water taking place, and that's what helps to keep this area relatively low temperature. So we're going to take a second to think about the common unfoliated metamorphic rocks. These are rocks that form in areas where there is relatively, well, there's no dominant pressure. So that means the minerals aren't made to align. And what you'll notice is when we look at the types of rock, we'll see that we're very, very limited in the types of rock we talk about. So if you metamorphose a basalt, you can end up with a greenstone, an amphibolite, a granulite, or an eclogite, or a hornfels. Okay. So if you find a greenstone, you know the protolith has to have been a basalt. If you find an amphibolite, the protolith has to be a basalt. Granulite has to have been a basalt. Eclogite, it has to have been a basalt. In the case of hornfelses, if you find a hornfels, the protolith could essentially be anything. So the protolith for a hornfels, now I know I've written basalt and shale here, those are the most common protoliths. However, in theory, you can metamorphose a granite, it will give you a hornfels. You can metamorphose a peridotite, it will give you a hornfels. Okay. The only types of rock that you cannot metamorphose to give you a hornfels are sandstones and limestones, because if you metamorphose a sandstone, it gives you a quartzite. If you metamorphose a limestone, it gives you a marble. So in the case of these rocks, there's no preferential alignment of the minerals, and they are most commonly associated with contact metamorphism, with the exception of eclogites. Eclogites are associated with, sorry, I'm going to go backwards. Eclogites are associated with the deep, okay, sorry about this guys, I'm having trouble going back through the slides. There we go. Eclogites are associated with the deep metamorphism of the subducting oceanic crust to very, very high temperatures and very, very high pressures. So those are the common unfoliated rocks. So here we go. So this is a greenstone, amphibolite, granulite. You can see that now there's a very weak foliation here, but on the whole it's unfoliated. Now in this case, these layers you see in this rock are not due to metamorphism. They are due to the original composition of the sediment that's metamorphosed. So the mudstones, layers of mudstone were metamorphosed to give hornfelses, and the layers of sandstone were metamorphosed to give these more tan-coloured quartzites. Then we have marble, eclogite, and quartzite. So you can see none of these rocks have any kind of layering associated with them. All the minerals in them are randomly orientated, and that's because they're forming in areas where there is no preferential stress. There's no one direction where the stress is at its highest. So, are there any other useful terms when it comes to metamorphic rocks? Well, just as igneous rocks can be porphyritic, metamorphic rocks can also have crystals that are noticeably larger. So, that's referred to as porphyroblastic. So, in the case of porphyroblastic rocks, the large crystals are called porphyroblasts, and the finer material surrounding them is referred to as the ground mass. We also have the term granoblastic. That simply means that your metamorphic rock has essentially a consistent and equal crystal size. So in a granoblastic rock, all the crystals will be approximately the same size. It's very, very common in rocks like quartzites and marbles and granulites and hornfelses. Then we have the terms associated with layering, these foliations. So if it's not one of these three types, we simply refer to the rock as foliated. However, there are three distinct types of foliation. The first type is referred to as a slaty cleavage, and this is when you get a parallel alignment of fine-grained platy minerals, especially very, very small crystals of mica and clay. Then you have a schistosity. That's produced by the parallel alignment of larger crystals, so medium to coarse-grained crystals of typically muscovite or biotite mica. And then finally you have a nicicity, and that's when we have a foliation which forms due to the parallel banding of the rock. So you end up with these light and dark bands. The light bands are called leucosomes, the dark bands are called melanosomes, and essentially the rock looks a little bit like a barcode. So what happens if the temperatures and pressures keep rising? So obviously, as you increase the pressure and temperature, eventually you're going to reach a point where you exceed the melting point of a mineral, and the rock is going to start to melt. So as the rock begins to undergo this process, we're going to see noticeable changes in the character of the rock that's going to suggest the rock is melting. So melting of the rocks is obviously only associated with the highest grade metamorphism, so it's only really associated with rocks like gneisses, granulites, and sandanites, which form at the highest temperatures. So these three types of rocks will typically have felsics, that's quartz and feldspar, and mafic, that's amphibole and pyroxene, rich regions, and the felsic regions will begin to melt first. So the minerals here, quartz and feldspar, have the lowest melting point, so when the temperature gets high enough, they will begin to melt first. And so what you end up with is a rock that's essentially partially melted. So it's partially igneous and also partially metamorphic. So it kind of sits in this grey area between these two classes of rock. And so what geologists decided to do in order to avoid an argument was simply say, all right, we know it's a bit of a mixture of both, so what we're going to do is we're going to classify it as a completely independent type of rock. We are going to call it a migmatite. So here is a nice migmatite here. So you can see in this piece of rock here we have these distinct layers, we have these dark bands, and we have these lighter coloured bands as well. So this over here, this would be a relatively standard looking piece of gneiss. What you'll notice though is as we go from this piece of rock into this region here, you will see that any layering, so follow this layer across here, just disappears. Same with this layer here, follow it across here, just disappears. So what we're seeing here is the layering, this banding that we get with these gneisses, just disappears and breaks down. So this tells us the rock is melting. And so when we get this kind of convoluted, so over here we can see the layering has become very, very tightly folded. Or when the layering disappears altogether and gets broken up, we know our rock is melting. And so we know at that point we have a migmatite. So now let's think about foliated metamorphic rocks. In fact, nope, let's not think about foliated metamorphic rocks. Let's take another couple of minutes. So stop the video here, get up, have a walk around, go and get a glass of water, and come back to me in a couple of minutes' time, please. Okay, so foliated rocks are produced when you have a preferential stress. That means essentially the rocks are being pushed hard from one direction or one alignment. And that's going to cause the minerals to fall over. Just like if you take a line of dominoes and you push them, the dominoes fall over. The process of you pushing the dominoes in one direction, that is your preferential stress. And so that's what's causing the dominoes to fall over in one direction. Minerals can do the same thing. If you put a preferential stress on the rock, like you squish it from the top and the bottom, well, you will make the minerals, so you squish it north-south, you will make the minerals align east-west. And so that's all we're saying. So foliated rocks will form in environments where you have compressional forces. And we've already discussed where those environments are. That's regional metamorphism and subduction metamorphism. In the case of regional metamorphism, you have two big pieces of crust banging into each other, and you have exactly the same thing in subduction metamorphism. And that's going to produce these principled stresses, where the stress is stronger in one direction than another. So that means you can end up with two distinct types of foliation. And these types of foliation are referred to as lepidoblastic, and that's when the foliation consists of platy minerals like the micas. That's essentially like pages in a book. One page stacked on another, stacked on top of another, stacked on top of another. And then we have lineated or nematoblastic metamorphic rocks. That's when the fabric is made from very long, slender crystals, just like holding a bundle of pencils. So in order to make the foliation happen, you can either simply push the minerals over, so that's essentially a physical process, or you can essentially make the minerals when the rock recrystallizes, so when one mineral becomes unstable and it changes into a new mineral, when that new mineral grows, it will preferentially grow at 90 degrees to the principal stress. So once again, if I'm compressing a rock from the north and the south, when the rock begins to recrystallize and new minerals form, those minerals will preferentially grow east-west, 90 degrees to the principal stress. So here's the basic idea. So here's a foliated or lepidoblastic metamorphic rock. We can see we have randomly orientated minerals, and we're squishing this rock from the top and the bottom, and we can see the minerals are aligning themselves east-west. So we're squashing north-south, and the minerals align themselves east-west. So when you look at a lepidoblastic rock, you will be able to follow the foliation across the ends, along the sides, but on the top there will be no foliation. Okay? Once again, just like pages in a book, you can see the edges of the page along the bottom and top of the book, along the sides of the book, but not on the top or the back of the book. So then we have lineated or nematoblastic rocks. These are rocks that are formed from elongate, so long, slender crystals. Think of them like a pencil. Think of it just like holding a bundle of pencils together in your hand. So when we look at lineated or nematoblastic rocks, we can see the layering on the side. We can see the layering on the top and the bottom, but we cannot see any layering on the ends. So that's how we tell the difference between a lepidoblastic and a nematoblastic rock. So lepidoblastic rocks, you see the layering on the ends, the sides, but not the top or bottom. In a lineated or nematoblastic rock, you'll see the layering on the sides, the top or bottom, but not the ends. So in terms of foliated metamorphic rocks, once again you can see they're dominated by mudstones, shales, and basalts. So if we take a shale and you metamorphose it to relatively low grades, so not very high temperatures and pressures, you end up with a slate. If it's a shale, you metamorphose it to intermediate grades, you end up with a phyllite. Increasing the metamorphic grades, your shale will turn into a schist. And then finally, as you get to very high metamorphic grades, your shale will break down and give you a gneiss. If you have a basalt and you take it to increased pressure and temperatures, the minerals that form can form an amphibolite schist. So amphiboles are long, slender crystals, so you're going to get a rock that looks like this. Or you can have a blue schist that forms at subduction zones. It's only when you get to very, very high temperatures and pressures that rocks like granite can actually be metamorphosed. So when you take a granite to low or moderate temperatures, the granite's just going to sit there and do nothing. However, when you take granite to very, very high temperatures, it can break down and it can also form a gneiss. So gneisses come in two different varieties. There's paragneisses and orthogneisses. Paragneisses are formed from the metamorphism of a sedimentary rock. Orthogneisses are formed from the metamorphism of an igneous rock, and you will not be able to tell the difference when you look at them in hand specimen. So here we go. So slate, phyllite, schist, gneiss. So this is what happens when you metamorphose a mudstone, like a shale. You'll notice so the slate has distinct layering, but the crystals are super fine, you can't see them. That's because all that's happening is you're just physically pushing over the clay crystals until they all lie parallel to one another. So hence the fact you end up with a layering. Now by the time you make it to the phyllite, you'll notice the rock has an ever so slight shine to it. It's got a bit of a sheen. And that's because the crystals of clay are breaking down and they're starting to form very, very small crystals of mica. These crystals of mica are still not visible though, but you do get the slight shine on the rock that tells you the mica crystals are there. We're going to pause for a second because it's time for the code word. The code word is soccer, S-O-C-C-E-R. So then we have schists. Schists are made from much coarser crystals of mica. You can actually see the individual crystals now. It has a very shiny appearance. So schists tend to actually have an appearance that looks something similar to tinfoil. And then we have gneisses. So gneisses, as you can see, have this very, very distinct banding of dark bands, the melanosomes, and light bands, which are called leucosomes. So slates, phyllites, and schists can only form by metamorphosing a mudstone. Gneisses can form from the metamorphism of a mudstone, but also from the metamorphism of rocks like granites. Now, blue schists can only form when we metamorphose a basalt. Okay. Now, blue schists are named blue schists because, obviously, as you can see, the rock has this very, very distinct blue colour to it. It's caused by the minerals glaucophane and kyanite. It took me a second to remember what the second one was there. And you can see it's just about visible here. You can see you have these layering. You can actually see the layering there. It's rather convoluted. It's a bit messed up, but nevertheless, you can see that you do have these distinct layers. You can pick one out there. You can pick a few out down here as well. Now, if you have a lineated rock, that's a rock that consists of long, slender crystals, you will end up with one of these lineated metamorphic rocks. So all of these rocks are essentially based on textures formed by platy minerals, like pages in a book. This is a lineated rock that's formed from essentially elongate crystals, like pencils. So in this case, you can see it's a bit weak, but you can just about make out the lineation. It's orientated along that line there. Okay, so you can make out the lineation on the top, which is running approximately that direction. You could see the lineation on the side down here, but when you look at the end, you cannot see the lineation there. And so that tells us this particular rock is essentially made up of long, slender crystals. All right, everybody. Well, that's it for part one. I know we've gone a little bit longer than the standard 1.5 hours, but what I've done is I've taken a little bit of, I've taken the 15-minute chunks from the first or second lecture that we didn't use, and I've applied them to this lecture so that we could make up the time that we needed. All right, so remember to make a note of that code word and keep an eye out for the second lecture appearing next week.